There we go. Hi everybody, this is the stoichiometry and vacuum filtration calculations video. So this should be similar to the data you have uploaded, and I'll be going through the example line, doing all the calculations. The calculation should also be written out for you in the lab data as well. So all of the measurables have already been written down. So the volume of KCl, the volume of AgNO3, the mass of the filter paper, and the mass of the filter paper and precipitate that was recovered. So the first thing, very easy, is how much actual precipitate did we have. The last thing we measured is the filter paper with the precipitate on it. So then the difference between those is going to be the mass of precipitate that we actually recovered. So very easy, straightforward calculation. We're doing subtraction, so we care about the number of decimal points. So that has 2 decimal points. This has 2 decimal points. Our answer needs to have 2 decimal points, which it does. Okay, so easy place to start. Now, moving on to the actual stoichiometry calculations. A lot of this, the tables are broken down to give you kind of one thing at a time or into single steps to deal with. That way, you don't have to do huge long calculations all at once. So a lot of the stuff is actually going to be copied from up above. So the volume of KCl is 69.2. The volume of AgNO3 is 99.2. There we go. The molarities on the bottle were both 0.100. That was given. It was what was on the bottle. And this experiment is specifically set up so that KCl is the limiting reagent. I'll talk about how we can see that in just a minute. So our next calculation. So let's use the little diagram in the stoichiometry PowerPoint to help walk us through some of these. I'm not going to fill in all of the words, but I'll use the shapes. And if you go look at the slides, you should have all of it filled in as well. So we have volume of KCl, and we want to get to moles of KCl. So all we have to do is use the molarity, and it'll work out for us as our conversion factor. So start with the 69.2 milliliters of KCl. And what you'll notice is all of these things that I'm writing have all 3 parts: number, unit, and chemical label, so that we know what compound we're discussing. In order to use the molarity, we will need our volume in liters. So the first thing I'm going to do is convert that volume to liters. And actually, I'm just going to worry about units right now. I'll go back in and fill in numbers. So our milliliters of KCl cancels out. We're left with liters of KCl. We want moles of KCl. So we need to get liters to cancel out. So we need liters on the bottom here. We can convert liters to moles based off of our diagram. And now we're at moles of KCl, which is what we wanted. So we've gotten all of our conversion factors that we need. Milliliters and liters, that's just a metric conversion. Hopefully you guys have that by now. Anytime we see moles and liters, that's a molarity. Well, we were given our molarity, and that number will always go with the mole part of that conversion factor. The liter will get a 1. So we do this math, and we get 0.00692 moles of KCl. We should check our significant figures. we're doing multiplication division, so we care about the number of significant figures. This has 3. This is a metric conversion that we don't count. This also has 3, so our answer should have 3. These are leading zeros that don't count. 1, 2, 3 significant figures. So that number is fine. We don't need to round it at all. So that's how we get our moles of KCl. We can do the same thing to get moles of AgNO3. Start with the volume we were given. Convert to liters. So the math and the steps are exactly the same, but the units and the chemical labels, are what's different. And that's why I always recommend writing those with it. So you have all of the information you need together. And we'll get 0.00992 moles of AgNO3. 3 significant figures. Don't worry about those. 3 significant figures. So this should and does have 3 significant figures. There we go. So at this point, we can determine our limiting reagent. Again, you were told it's KCl, but because we know these react in a 1-to-1 ratio, the lower of these values will be our limiting reagent. So 0.692 is lower than 0.00992, which means KCl is our limiting reagent. To truly calculate it, we would do things a little bit differently, but that's starting to get more complicated than we need to for this course. Theoretical moles of precipitate. So once you know your limiting reagent, you don't care about the numbers for the excess reagent. So basically, none of these are going to be important for any of our calculations. The data is still important. It's still important stuff to have, but all of our calculations are going to start from the volume of KCl that we have. So to put this little diagram back up. There we go. So we're going to start from a volume of KCl. Let's see if I can fix that K. There we go. The next thing we want to get to is moles of a precipitate. So we're of a different chemical. So we're going to be over here, and we need moles. So we need to use the molarity to get to moles of KCl, and then we need to use the coefficients from the chemical equation to figure out our precipitate. So this is a double displacement reaction, so you guys should be able to figure out the products. And be able to balance it. So we mix KCl and AgNO3 in a double displacement reaction, meaning, fix that. Potassium is going to go with the nitrate, and silver is going to go with the chloride. Potassium's a +1, chloride's a -1, silver is a +1, nitrate is a -1. So we'll get KNO3 and AgCl. So again, make sure you can predict those products. If we go to balance it, One potassium on the left, one potassium on the right, that's balanced. One chlorine, that's balanced. One silver, that's balanced. One nitrogen, that's balanced. 3 oxygen. So everything was already balanced for us, meaning all of our coefficients are just ones. And since they're not written, we don't need to write them in. I'll go ahead and show them for a minute. But everything's 1 to 1. So with all of that said, since we know everything's 1 to 1, we can now do our calculation. Starting from 69.2 milliliters of KCl. I should have done this there. Our products were KNO3 and AgCl. If we look at our solubility rules, nitrates are soluble, potassium is a group 1 metal, so it should be soluble. So that thing should be soluble. Chlorides are usually soluble except when they're paired with silver. So AgCl is our precipitate. Again, you should be able to identify this by using what you learned last week and moving forward with this week. So in order to use volume to get to moles, we need our volume in liters. But liters of KCl is not the unit we want to end with. We want to end with moles of AgCl. So we need to get that to cancel. We can convert liters to moles. And that leaves us with moles of KCl. We want moles of AgCl. Again, this is why that chemical label is important. We are at moles, but not of the right compound. Moles of KCl to moles of AgCl. Now we're at moles of the compound we want. Now we can go back and fill in our numbers. Metric conversion. Our molarity was given. Moles over moles means we have coefficients. Those coefficients were all 1 to 1. So we can fill that in really easily. And we'll get 0.00692 moles of AgCl. This is the same number as the moles of KCl that we had earlier, but that's only because it's a 1 to 1 ratio. If that ratio was anything different, then this number would change. Okay. So let's get rid of that for a minute. Now, our last calculation for this table is the theoretical mass of the precipitate. So now we need to get all the way over to this box. So we'll do the same 2 steps, and then we'll use the molecular weight of AgCl to convert moles to grams. So that's the conversion factor I'm going to add on right here. Our moles cancels. We're left with grams of AgCl, which is what we wanted. Anytime we have grams and moles in the same conversion factor, that means we're using the molar mass or the molecular weight or the formula weight or whatever interchangeable terms you want to use. There's a bunch of different ones. So you should be able to find the molar mass of AgCl, find the molar mass of silver, find the molar mass of chlorine, add those together, and you'll get something, depending on the exact periodic table you use, something around 143.32. So then we can do this new calculation. And get 0.99177444 grams of AgCl. Again, we should always check our significant figures. This has 3. This is a metric conversion. This has 3. The coefficient conversions, we don't care about their significant figures. And the molecular weight in this case has 5. If you should always make sure that your molecular weight is not limiting. You can almost always find a periodic table with enough significant figures to make something else your limiting value. So we need to limit this to 3, which means we'll round after the 1 and get 0.992 grams of AgCl. So again, all of this is basically just dimensional analysis with a fancy name called stoichiometry. If you pay attention to your units, follow your steps, you'll get to exactly the same point that you need to be at. So let's clear all these and scroll down. There we go. So now what we wanted out of all of this was our percent yield. So the actual mass of the precipitate is what we recovered, the 0.95. Oops, 0. There we go. The theoretical mass of the precipitate is the mass we calculated, 0.992. So our percent yield, if we remember our equation, is actual over theoretical times 100%. So our actual was the 0.95, theoretical is the 0.92, and we'll get 0.95 over 0.992. Again, units and labels are still important because these have to be the same unit of the same chemical to cancel out correctly. So the only units left are your percent. We do that math. And actually, because we rounded this value, I'm going to go back to that full value, the 0.9917744 that I still have in my calculator. So 95 over 0.9917744 times 100. And we get a whole bunch of significant figures. This has 2, this has 3, so we're limited to 2 significant figures. We'll round that to 96% yield, which is pretty good. Oops, not, there we go. So that's the percent yield for the example calculations. When you do this, you would have values for trial 1, 2, and 3, and then you can take the average of those, add them all up, divide by your total number of trials, and you'll get your average percent yield. And that's really all there is for this. Again, stoichiometry sounds big and scary. It really isn't. There's nothing to it. It's just dimensional analysis. So you've got this video of me going through the calculations. They'll be typed into the lab data that's uploaded. If you're still struggling, reach out to me and I can walk you through them all again and we'll get through it. But that's all of the calculations for this experiment. So good luck.